think it's great. It's very exciting to have this workshop specifically about ICCU or ICCCU. We can discuss this later. So I think we have a few. The program is quite tight, and I think the idea is we have very brief chat, a brief presentation about basically the current research updates about the integrated CO2 capture utilization technologies. I think based on the program, we have the first presentation will be given by Professor Jun from University of the Basque Country. And Jun, can you start sharing your screen?
Yeah, okay, thank you. Then I can begin. I will show you.
Yes, yeah, you can start.
Yeah. Okay.
I suggest we could, the presentation, the time is 15 minutes. I suggest we could have about 12 minutes presentation, then
Okay.
allow maybe 2 or 3 minutes for discussion. I can see your slide. If you can go to the, oh, that's great, yeah. Excellent.
That's correct. Okay, okay. Good morning or good afternoon, depending on the show. Thank you very much, Dr. Wu, for your invitation to participate in this interesting workshop. I am a professor of chemical engineering at the University of the Basque Country in Spain, and our group is called Chemical Technologies for Environmental Sustainability. To begin, just a bit of our history. We founded the group in 1988, mainly focused on engineering of absorption and chemical reaction, applying catalytic technology to the removal of contaminants and cleaner chemical production processes as a convenient roadmap toward chemical sustainability. Since 2000, we were very active and recognized in the development of lean Linux traps under the concept of reaction-induced desorption. It was in 2015 when we transferred our expertise with similar strategies for conceptually adjacent chemistries to exploit the concept of reaction-induced desorption to lower temperature requirements for CO2 capture and release. We focused then on the power-to-gas technology and carbon capture and utilization processes. The integrated CO2 capture and utilization process to produce methane is promising as it reduces the cost of the overall process by eliminating transportation and storage of CO2 because the two steps are carried out on site in a cycle manner. To carry out the ICCU process, a dual function material has to be used. The cycle is represented in the graphical cover of an issue of catalytic science and technology for one of our last papers. A factory that generates big amounts of CO2 proceeds to its capture in the dual functional material, where it's recycled to methane, which again is used as the fuel in the main production. At present, we are working on this technology for being applied in a company specialized in energetic materials, which has 2 wind farms within its industrial territory and has a combustion system that uses natural gas as fuel. Conventional post-combustion CO2 capture schemes require a solvent capable of efficiently capturing CO2 from exhaust streams with around 10% CO2. DFMs are bifunctional solids composed of 2 components integrated, an adsorbent with adequate basicity to allow CO2 absorption, and metal nanoparticles to carry out the hydrogenation of CO2. During the CO2 absorption step, the adsorbent is progressively saturated with CO2. The metal particles may be partially oxidized, resulting in the formation of a passivation layer. Subsequently, after feed switching to green hydrogen, The hydrogen reduces the metal nanoparticles back to the metallic state, which become active for methanation. CO2 molecules desorb or spill over towards the metal nanoparticles, being hydrogenating to methane. Thus, a single solid is loaded in a reactor, and the operating conditions are modified at regular intervals to switch between capture and methanation modes. Practically speaking, one would need two parallel units to be able to treat effluents in a continuous mode by switching the respective units between the capture and methanation modes. The process meets condition of circular economy, providing a net neutral carbon emission cycle. From qualitative and quantitative analysis of different compound concentration profiles, together with FTIR analysis for identifying different compounds, we have proposed a complete reaction scheme describing CO2 adsorption and hydrogenation, which is represented in this slide for ruthenium catalyst with calcium and also sodium adsorbents. The mechanism is consistent with the amounts of CO2, methane, and water detected at the reactor exit along the adsorption and hydrogenation period. The onset of CO2 concentration profile, red line in the figure, is detected after some time from the beginning, revealing that adsorption sites are becoming progressively saturated and some CO2 started to leave the reactor without being stored. The absorption of CO2 is accompanied by the release of water, blue line, from the carbonation of the hydrated oxides. Hydrogen injected in the gas stream reduces the stability of the carbonates and favors the decomposition and subsequent conversion to methane on ruthenium sites. The formation of methane, grid line, is immediately detected with hydrogen injection, whereas water is somewhat delayed. Reactor modeling is a very useful tool in the design and scale up of commercial reactors, enabling prediction of the system behavior under different operational conditions without the need for expensive and time-consuming experimentation. The model we developed is based on the previous mechanisms and consider fractional coverage factors of for absorption of CO2 and water. Theta equals 1 for the catalyst fully regenerated and equals 0 for the, 1 for catalyst fully saturated with CO2 and 0 for the fully regenerated, and values in between proportional to the partial saturation state. The reactor was modeled as a dynamic one-dimensional isothermal heterogeneous plug flow reactor with axial dispersion. Solving the system of partial differential equation by finite differences returns the evolution of the concentration of CO2, methane, and water, which are represented in the figure on the right in color lines, together with the experimental data in black lines. The chart below corresponds to the covering factors of CO2, water, and unstable bicarbonates for the last zone of the reactor. Although this assessment corresponds to some determined operational condition, validation was checked for an extended range of operational conditions, temperature from 250 to 400 degrees C. This validated model can be used to simulate different operational scenarios. As an example, we can inquire about the effect of varying the absorption time to regeneration time ratio on the dynamic of the cycle process. The evolution of CO2 conversion, hydrogen conversion, and methane production are shown in these 3D pictures for different ratios. Under a short absorption and long regeneration time, there is not enough time for the DFM to be saturated with CO2, which will be easily reduced during the long regeneration period, achieving high CO2 conversion and full regeneration of the DFM. The opposite occurs under a long absorption and short regeneration times. Then the absorption time allows full saturation of the DFM with CO2, but the short time for regeneration only provides a moderate use of the supplied hydrogen with limited conversion. As the third scenario, which is the optimum, with the absorption period allowing full saturation of the catalyst with CO2 and also extending the regeneration time to achieve complete regeneration, the operation will supply maximum efficiency with higher production of methane. Let me finish summarizing other relevant contributions from our group. In addition to the extensive screening of conventional nickel and ruthenium-based DFMs, we found that seria-supported lanthanum nickel perovskites are good precursors for DFM materials because of regulating the exsolution of nickel particles from mixed oxides. Moreover, the controlled substitution of lanthanum by calcium leads to a concomitant gradual change in the density and strength of basic sites, which is crucial for this process. We advance also the state-of-the-art in the reaction transport models and brought together a powerful combination of spectroscopic and kinetic protocols to elucidate the limiting step involved in detaching CO2 from binding sites and then reacting it with hydrogen to facilitate its desorption. We provided basic engineering tools to predict the performance of the process and to design smart reactors, including the heat management for industrial implementation. Or in short, we continue bringing this technology much closer to commercial reality through systematic improvements in stability and methane yields and in the development of spatiotemporal performance models to create the framework for further operational and conceptual developments. Lastly, thanks again to the organizer, Dr. Wu, to all attendees to the workshop, to financial supporters, and likely to all researchers in my group. Thank you very much.
Thank you, John. I think that's excellent. It's about the ICCU and the methanation and especially some modeling work. I think I didn't see any modeling work previously, except your group. So any questions for John? You can raise your hand or just open.
Thank you very much.
Sorry, who is asking? I can see Melis, your hand there is up here.
Yeah, I have a quick question.
Yeah.
Very nice work. I'm really interested in the modeling results shown. I'm just curious. So in terms of once you create the model based on experimental data, how well does that translate when you try the different conditions that you've been showing from your modeling results? In other words, how many experiments would you need to model the behavior of a DFM before you can use that for optimizing the operating conditions?
Yes. In our case, we did about 160 experiments under different conditions because we modified not only times for both periods, but also concentrations during the absorption period, also different concentration of hydrogen during the regeneration periods, and of course the range of temperatures between I said 250 degrees and 400 degrees. Then there are many different, because in other case it will be almost impossible to check the validity of the model with the experimental data. Even taking into account that our model is our reactor model is only one-dimensional model. Now we are doing for more than one dimension, and it's more difficult because we also have to take into account temperature profiles in all around the reactor. I mean, in different positions at every position, at every axial position of the reactor. We are following with that now.
That's great. I think this modeling work is really exciting. Yeah. Sorry. And I think due to the time limit, sorry, I think we need to move to the next presentation. You can write your question in the chat box, then John can answer it there. Okay, thank you.
Okay, thank you.
Yeah, our next presentation will be given by Professor Quarry. Quarry, are you there?
Yes. Can you hear me?
Great. That's great. You can start sharing your screen and you give the presentation.
Give me a minute. I have a problem here. All right. Give me a minute.
No worries. Oh, it's coming. That's great.
Give me a minute. I need to turn on my video.
It's okay. We can see your slides now. It's good.
You can see my slide now? Okay.
Yeah, if
all right.
you go to the presentation.
Are you able to see my slide now?
Yes, but we can also see your notes. So if you go to the...
Okay, give me a minute. Hold on. Minute. I have a problem here. Oh, still the same thing?
Yeah, I think maybe it's you are using two screens.
Give me a minute. How about now? Are you able to see my screen now?
No, when you can see your picture.
You see my pictures only. Oh.
Yeah,
How about now?
Yeah, we can see your print. Oh, that's good. Excellent.
Okay. All right. Okay. All right. So, good morning or good afternoon, everyone. Thanks, Chunpei, for organizing this workshop. Thank you for giving me this opportunity to share part of my work with the audience, on my work for this innovative sustainable catalyst system for CO2 capture and utilization. So for this talk, I will present 4 topics: CO2 utilization, hydrogen production with CO2 capture, simultaneous CO2 capture and utilization, and plasma catalysis. So let me start off with my first topic, CO2 utilization, on CO2 reforming with methane, or simply we call it dry reforming. Singapore is a small country, but it has so much waste, such as food waste or sewage sludge. This waste can be converted into biogas using anaerobic digestion. Since biogas contains 65% of methane and 35% of CO2, this biogas can be converted to biohydrogen using CO2 reforming with methane. My research group has been working several types of catalysts, most importantly on the core cell catalyst to convert this CO2 with methane to form syngas. So we use a core cell catalyst, multi-core cell catalyst, sandwich core cell catalyst, and multi-core hollow cell catalyst. Our catalyst has been found to have high nickel dispersion, high porosity, bifunctional property, high activity, high cold resistance, and most importantly, it is easy to be synthesized in large scale. I'll just give you one example here. So this is the multi-core hollow cell nickel catalyst. And you can see from here that this catalyst has been found to have a very high methane and let me see. I can just turn on my video. All right, can have methane and CO2 conversion, almost reaching equilibrium conversion, and the catalyst has been found to have no almost no cold resistance for more than 600 hours. Because of the silica cell surrounding the catalyst, and the catalyst can be fully regenerated. So after we have found the catalyst, we try to integrate that with the membrane. So this is the catalyst that I use, the perovskite catalyst, and you can see that the CMR is the catalytic membrane reactor, PBR is the pet bed reactor. You can see that catalytic membrane reactor perform much better than the pet bed reactor in terms of activity and in terms of stability. In fact, the TGA result shows that the catalyst from the catalytic membrane reactor has almost no negligible carbon deposit on the catalyst, but the catalyst from the pet bed reactor has quite a lot of carbon deposit on the catalyst even after 40 hours of reactions. We also integrate our catalyst with the palladium silver alloy membrane reactors. And you can see from here that the performance of the catalyst can be beyond the equilibrium conversions. From the pet bed, we achieve about 50% conversion, but once you use the catalytic membrane reactor, it can increase beyond the equilibrium conversion to 70% conversion. And we can also achieve 80% recovery of pure hydrogen, almost 99.9% hydrogen from the reactor. And the catalytic membrane reactor perform quite stable during the reactions. Let me show you our reactions for the CO2 hydrogenation reaction, especially for CO2 methanation. So we have tried to increase the catalyst specificity of the catalyst using nickel SB15 catalyst. And as you can see from here, without magnesium, this is just a normal nickel SB15 catalyst. Bidentate format is formed, but once we use magnesium, we will form monodentate format. And we have found that monodentate format can be converted towards methane much faster than bidentate format. So that shows that medium side basicity is can convert methane much faster than big basic sites. We also try to combine the CO2 methanation with the membrane. So this is the propane hydrogenation reaction. During the reactions, you produce hydrogen, and hydrogen will permeate through the membrane. And on the other side, we have these CO2 methanation reactions. So we couple these two reactions together. And as you can see from here, this is the pet bed reactor results, and this is the catalytic membrane results. And for CO2 methanation, catalytic membrane reactor perform much better than pet bed reactor in terms of activity and in terms of stability. Next, I will show you a brief result for the hydrogen production with CO2 capture for biomass gasification. Now, we can produce from biomass, we can produce hydrogen production with CO2 capture, but it requires two integrated stages. The first stage is to convert tar with steam to form syngas, and after that, the CO in the syngas can be converted in using the water gas sieve reaction to form to get more hydrogen yield with CO2 captured. We have synthesized this LSNF perovskite catalyst, where in the A side, the strontium is the lanthanum is substituted by the strontium to form a stronger basic catalyst. And you can see from here that the performance for this tar conversion is very high, and almost more than 90% conversion, and it is very stable during the reactions. And the reason why LSNF perovskite is good is because strontium can absorb steam at very high temperatures, and steam can be dissociated into hydrogen, and the hydrogen that produced can then convert coke on deposit on the catalyst, so that it can increase the activity and stability of the reactions. We can then combine this tau reforming using membrane. Using this, we call it peroxide membrane, and oxygen from the air can be permeated to the peroxide, so that it can involve in the oxidative steam reforming of the tar to increase the energy efficiency of the reactions. We have synthesized this BBCN membrane, which has very high oxygen permeation ever reported in the literatures, and it has very high chemical resistance under steam and hydrogen. And we perform this tau reforming in the catalytic membrane reactors, which shows much higher activity and stability compared with those PET reactor. Next, I will show you our some result on the water gas shift reactions for hydrogen production with CO2 capture. We have synthesized this nickel magnesium pyrosilicate catalyst to form this nanorock cell catalyst. And the performance of the catalyst can be done at 650 degrees Celsius, very high temperatures water gas shift reactions. So you can see from here, nickel magnesium pyrosilicate nanotubes can perform much better than those without magnesium. Without magnesium, the catalyst deactivate under the hot steam. And the spent catalyst for the nickel magnesium pyrosilicate is very stable because of due to the nanotubular structure of the catalyst. We can then integrate these reactions, water gas shift reaction with the membrane. And the reason why we want to do that is because during the reaction, once hydrogen is produced, hydrogen can be permeated across the membrane, palladium layer membrane, to get very pure hydrogen. And furthermore, by removing hydrogen from the reaction stream, we can shift the reaction equilibrium to much higher hydrogen yield, and the CO2 that is produced can also be captured directly. So we have combined this, integrate this catalyst with the palladium alloy membrane, and in order to get pure hydrogen from the reactions. And as you can see from here, the reaction can be increased beyond the equilibrium conversion from 50% conversion to much more than equilibrium conversion to about 75% conversions. And not only that, we can also get minimize the methanation from the reactions, and can from 7% conversion to less than 1% conversions. And we can also recover quite high amount of hydrogen from the reactions. Next, I will show you the our summary result on this development of this catalyst system for simultaneous CO2 capture and utilization using membrane separation for reverse water gas shift reactions. So this is our membrane. It's made up of the dual phase mixed oxide membrane, where the oxide can permeate the CO2. The molten carbonate can permeate the CO2 across the membrane, and the oxygen can be permeated across the using the peroxide membrane to the other side. And our membrane, this membrane can permeate CO2, a very high amount of CO2 flux, permeation flux at around 700 degrees Celsius. And this our membrane also very stable for at least more than 90 hours of reactions. So we can use this membrane to capture CO2 from the flue gas. And this is our result showing that we can combine, this is the flue gas coming in, the CO2 in the flue gas can be captured across this membrane. And once the CO2 is permeated across the membrane, we can use this CO2 for the reverse water gas reaction to form CO. And we have found that our catalytic membrane reactor can achieve very good CO selectivity, almost 100% CO can be produced, and our membrane is very stable during the reactions. Next, I will show you some results on the chemical looping that we have tried to develop. So in this CO2 chemical looping, we use calcium oxide to capture the CO2 to form the calcium carbonate in the first phase. After that, we can then flow the twist the reactors to flow methane, and the methane can then react with the CO2 that is released during for dry reforming reactions to form a syngas. So this is the simultaneous CO2 capture and utilization. So I just show you one of the catalyst system that we have developed. This is the nickel Syria catalyst supported on zirconia, on calcium coated with zirconia. And we can see from here that the CO2 capture is very high when we have a Syria compared with those without Syria, and it's also quite stable. And after it has reached the saturation, we can switch the reactor to the methane mode, and the methane and the CO2 that is released can then react at the same temperatures. We do need to increase the temperatures at the same temperatures, and then we can do the dry reforming during the reactions. And the reaction is very stable and we can recycle this the CO2 capture and utilization many times. So let me try to show you the recent work that we have been doing on using plasma catalysis for CO2 utilization. Our group has been using this DBD plasma, sometimes we call it cold plasma, at room temperatures for CO2 utilization. And the reason is because this DBD plasma can be performed under very mild reaction conditions, but unfortunately, if it forms multiple products during the reactions. So to minimize this drawback, catalyst plays a very critical role in plasma catalysis to produce the desired product selectively. So let me show you one of the reactions that we're interested is to do reverse water gaseous reactions. So I can show you from here that our catalyst is during plasma catalysis at room temperatures, we can convert the CO2 to at around 60% to produce a very high amount of CO, about 90%, and also very stable during the reactions. Now, if you do this reverse water gaseous reaction thermally, it needs to be done at very high temperatures. At around 600 degrees, the CO2 conversion can only achieve 40% of conversions. So in conclusions, I have shown you that using the causal catalyst and basicity, nickel-based catalyst can be developed for CO2 reforming of methane and CO2 methanation for CO2 utilization, and for tar reforming and water gaseous reaction for hydrogen production with CO2 capture. And I also shown you that a catalytic membrane reactor can be developed for CO2 utilization, for hydrogen production with CO2 capture and simultaneous CO2 capture and utilization. And I also briefly show you that chemical looping and plasma catalysis are potential technologies for carbon capture and utilization. Thank you very much for your attention. I will welcome any question that you have.
Thank you, Corey. I think that's excellent presentation covering especially catalytic membrane reactor, which is quite specific. I think due to time limit, we actually over time now. So any question you can write your questions in conversation box, then Corey can answer it there. Okay, thank you.
All right. Okay, thank you. Thank you. Yeah.
We're going to move to the next presentation given by Dr. Changlei Qin from Chongqing University. And Changlei, I can see your slides now. Yeah. And Changlei, we make it within 10 minutes, okay? About 10 minutes. Yeah, we started time. Yeah, it's okay, but I can't hear you, Changlei. I can't hear you. I think there's in rooms there's settings, microphone setting. So I think besides the mute function, if you
can you hear me now? Can you hear me now?
Yeah, it's good. I can hear you. Yeah.
Okay, okay.
You can start sharing your share your screen again.
Yeah. Wait for 1 minute, okay?
Yeah.
It's okay now?
Yeah,
Sylvie?
good. You can start. Yeah.
Okay. Hello everyone. I'm Chang Lei Xin from Chongqing University. I'm very glad to have the opportunity to share our latest progress on integrated CO2 capture and utilization in CQU 2022. Firstly, I want to give a very brief introduction about my research group. Actually, I got my PhD degree from the University of Queensland in 2014. Then worked in School of Energy and Power Engineering at Chongqing University. Firstly, as a lecturer, then as an associate professor. I'm also a member of key lab of low-grade and energy utilization technologies and the systems of Ministry of Education. My main research focus is CO2 absorption at lower, medium, and high temperature. I also extended the work to RCCU and absorption enhancer reforming for hydrogen production. And currently, I supervise 4 PhD students and 6 master students in my research group. Okay, this is a very brief introduction. Now let's turn to the research work. The research will be divided into 4 parts. The first one is background, followed by the RCCU methanation, RCCU dry reforming and methane, and the last one is very brief conclusions. Let's see the background. For the CO2 issue have been talked a lot, so I just skip it. For the conventional CCU, as we know, CO2 after emission will be captured, compressed, transported, and followed by the utilization or storage. Very clearly, it's a very long chain process which is complex with high cost. Also, there are several temperature swings, which means a high energy consumption. In contrast, the integrated carbon capture and utilization combine the capture and the utilization together. So these two processes can be completed in just one reactor at a constant temperature. So it's becomes simple and shows a potential high energy efficiency. According to the reducing gas, it be used in RCCU. RCCU can be divided into 2 categories. First one, RCCU using the light alkenes. For example, RCCU by the dry reforming of methane, and RCCU by oxidative dehydrogenation of ethane to ethylene. The other one is RCCU hydrogenation. And the 2 very common route is RCCU by reverse water gas shift and RCCU methanation. Okay, let's say RCCU methanation. RCCU methanation is a very common power-to-gas route. We know comparing to hydrogen, methane is very easy for transportation and storage. The next one is it can fully utilize existing infrastructures without any large-scale upgrading. The third one is if the CO2 is coming from air or biomass, it's a carbon neutral cycle. Finally, methanation actually comparing to other reactions is exothermic. So it means no external heat is required at all. So I think this is one important advantage of the RCCU methanation. For high efficiency RCCU methanation, the dual functional materials is very important. Based on our experience on CO2 absorption, we think lithium oxide silicate could be a very good solvent for the RCCU methanation, as it has good CO2 capacity with excellent cyclic stability. The stability is very good. Next one is the absorption and desorption temperature of 500 to 600 degrees. The temperature match kinetics of methanation also very well. So following this idea, actually, we propose lithium silicate as the solvent and catalyst support, nickel as catalyst, and ceria as isolator to prevent any potential interaction between the solvent and the catalyst. So finally, we prepare DFMS by successive loading of ceria and nickel on lithium silicate by the impregnation. We prepared 3 DFMs with different nickel loading, 2.5, 5, and 7.5. Actually, all these 3 DFMs show very similar morphology, elemental distributions, and even the phase patterns. But the DFM with 5% nickel shows have the highest surface area. Additionally, all these 3 DFMs, their CO2 capacity is all about 0.2 gram per gram during the cycles, and actually the stability is very good. Also, the desorption kinetics is rapid. Then we tested the RCCU methanation and the different temperatures. We say CO2 adsorption favor high temperature, a little high temperature, but catalysis favor a little temperature, lower temperature. After optimization, the reactions actually in 560 degrees is determined to be the best reaction temperature, and DFM with 5% of nickel show the best performance, which are the CO2 capacity of 5.4 millimole per gram, 98% CO2 conversion, and 96% methane selectivity. Also, during the reactions, we observe a much quicker CO2 release than the common desorption of CO2 from the solvent. To understand the mechanism of RCCU methanation, actually, we tested the DFM by in situ drafts. We observe the presence of methane, carbon monoxide, and fomate at a temperature as low as around 200 degrees. However, at such a low temperature, we know it's impossible for the occurrence of CO2 desorption from lithium silicate-based solvent. So based on this observation, actually we suggest the mechanism for the RCCU methanation is the hydrogen adsorbed via reactor with carbonate rather than gaseous CO2 to produce fomate. Fomate is an important intermediate. Then fomate will be converted to methane by different routes. The next one, we evaluated the cyclic performance of these materials, and we found the CO2 adsorption desorption performance is good, but there's slight oxidation of the catalyst, which may come from the product of steam. To mimic the flue gas impurities, actually we also tested the steam and the effect of steam and oxygen. We found the steam decrease catalytic performance, but oxygen helps reactivate the catalyst. It means when there are coexistence of the steam and oxygen, actually the performance of the DFM is as good as that without any of these impurities. This is very interesting and very interesting. The last one, we also compare the results with that in the literature. Actually, the DFM developed in our work shows balanced performance on CO2 capture, conversion, methane selectivity, and yield, and reaction kinetics. The third one is RCCU dry reforming methane. Different to the RCCU methanation. RCCU methanation, we know it favors a little lower temperature, but dry reforming favors high temperature, usually around 700 degrees. at such a temperature, calcium oxide is a good solvent candidate. However, at such a high temperature, it's very easier for the solvent and for the catalyst to be centered. So support will play a very important role to prevent the potential sintering of these materials. So in this work, we test the role of different support using the SPA15, the zirconia, Syria, and illuminate the 4 different support. We say the DFM supported on SBA have the highest surface area and pore volume. Its TPR profile is similar to the DFM supported on illuminate, which means these two actually have good interaction between the support and the catalyst. Likewise, we test their performance by the individual CO2 capture and individual dry reforming method. We say the DFM supported on illuminate is stable in cyclic reactions with a CO2 capacity of 0.5 gram per gram. Actually, this rate, their capacity is very stable. And in the dry reforming, actually the highest methane and CO2 conversion is 90% and 85%. And the other one, very interesting, is for the DFM supported on SBA. Actually, there are no any other carbon deposition found. So next one, we tested the RCCU dry reforming characteristic. We say for the DFM supported on SBA, there are almost no carbon monoxide is observed in the CO2 capture stage. However, for the other DFM, a large amount of carbon monoxide is produced during the CO2 capture stage. The reason is here, the CO2 will react with the carbon deposited during the previous dry reforming stage. We also tested the cyclic reactions. We say the DFM supported on SBA shows almost no change in 20 cycles with only slightly CO2 clearance during to the slow reduction of CO2 capacity. For the DFM supported on illuminate, there's some kind of methane conversion decrease due to the carbon deposition. Finally, for the DFM supported on illuminate, we say the CO2 capacity is very good. CO2 conversion also stable at around 78%, but there's a gradual reduction in the methane conversion. For the DFM supported on SB, the CO2 capacity is just half, but the CO2 and methane conversion is double. So more work still needed to optimize the synthesis and the performance. Okay, finally, a very short conclusion. The photon when we developed lithium or silicate-based DFM for RCCU methanation, it shows balanced CO2 capacity, CO2 conversion, and methane selectivity. Also, we suggest the reaction mechanism of the RCCU methanation using this DFM. The next one, we tested various energy support DFM for the RCCU by dry reforming method. Okay.
Thanks.
Okay, that's all. Thank you for your attention.
Thanks, Stanley. Again, due to a limited time, I think, Stanley, we're going to move to the next presentation. I think that's excellent work regarding the dry reforming, because the cook deposition is a big issue.
Okay. Thanks. Okay, thank you, Chunfei.
Our next presentation will be given by Professor Hu Jun from East China University of Science and Technology. Professor Hu. Professor Hu was clear. Yeah.
Thanks, Chenfei,
That's excellent.
for giving us this good organization, very good seminar, and so we can discuss some interesting things about ICCU. So I'm Zhong Fu, come from the East China University of Science and Technology. Today I'd like to talk about the synergistic promotions between CO2 capture and the in situ conversion. So as we all know that sorry, I can't see the, so I can't see the topics. So how can
you want to see the notes?
yes, notes, and also some, because these terms. Okay, let me try. And because of the path to the, sorry, this is very difficult for me because this line is covered my topics. Because we seldom use these zooms. Okay, let me try. And because of the net zero carbon aims, we try to use the CCUS to contribution the 15% of CO2. Sorry, there's different paths to net zero carbon, and the CCUS will contribute 15%. But we all know the CCUS challenges is the high cost and high energy conservation. And instead of this, and for the CO2 utilization, and we mainly focus on the currently most CO2 utilization are concentrated at the geological utilization, which is quite different compared with our topics today. And instead of using very instead of the CO2 utilization of geological utilization, we use the chemical utilization. That is we call that is the ICCC, because here we mainly focus on the chemical conversion. So I recommend use this abbreviation of ICCC rather than the ICCU, because we need the chemical conversion. And by skip this CO2 compression and the transportation, we have good advantages of the low cost, high variable products, as well as the low energy consumption, because we can use the efficient usage of the heat of the flue gas to supply the system, to supply the necessary of energy consumption of the conversion. But still, we have two challenges here. One is the conversion and capture and the conversion process matching, and another is dual functional materials. For the good capture and the conversion process matching, we should understand what is the characteristic of the emission, of the carbon emission from different sources. And for example, for the main resource of the CO2 emissions are coal-fired power plants and steel-making plants. They have quite different CO2 concentration, of course, and they also have different emission temperatures. So if we want to design ICCC process according to the characteristic of flue gas, we should be careful. So we briefly make the categories of ICC technologies into according to the operation temperature. For example, when the temperature is higher than 400 degrees C, that means the high temperature ICCC. By the thermal catalysis, such as the reverse water gas shift reaction is the main conversion reaction because its temperature is much matching with the high operation temperature, such as the 650 degrees C, and with the products of syngas, and further for the olefins and and aromatics and so on. And when the operation temperature is below 400, between 200 and 400, and also the main products can change it into methane and methanols. And for the depends on the different pressures. And for the low temperature ICCC, when the operating temperature is lower than 100 degrees C, such as the flue gas after desulfurization from the power station. So we can introduce the photocatalysis, electrocatalysis, and plasma catalysis to the different dessert products. So that is the different kinds of ICCC depending on the flue gas temperatures and operation temperatures. And here is the case. We are working on the high temperature ICCC for industrial flue gas. For example, now we're working on the hydrogen production industry. Although hydrogen is considered as the most green energy for the future, but even now, 99% of hydrogen produced from fossil fuel. That means per each ton hydrogen produced, we need emission 6 to 10 tons CO2. So how can we treat this carbon? So we take this carbon as a resource and using the hydrogen to reduce the CO2 in situ, and using the high temperature flue gas as the energy input, and this temperature will as high as 750 degrees C, and by using an isothermal consecutive reaction in the same one reactor, first the high temperature inside into this column, and the first step is CO2 capture, such as using the calcium looping, and after the calcium oxide is saturated, then we change it into hydrogen, and then comes to the next step is the CO2 conversion with the calcium reverse water gas shift reaction. We can produce CO, and if we have enough hydrogen, then we can produce the syngas. So based on this idea, we fabricated the dual functional materials, and these dual materials are porous metals, calcium-based DFMs, and which is very easier to be scaled up, and the CO2 capacity is as high as 9 mole per kilogram, and shows very high stability. And the ICC syngas is achieved with the CO2 conversion efficiency of larger than 90%, and the CO2 selectivity almost 100%. And they shows also very stable adsorption and conversion stabilities. And we also proposed a redox heat junction mechanism, just like photocatalysis. The two dual metals can form here. Two metals, they have a redox electric potential matching, and they can form a new Fermi energy, which can promote the escape of electrons, and then to enhance the catalytic performance. And based on these works, now we are working together. We are incorporated with the China Sinopec company, and maybe next year we will establish a pilot scale demonstration next year. So that may be the first ICCC demonstration. And another thing is that dual functional materials. And today I'd like to talk about the very interesting findings about the dual functional materials, because the adsorptive sites and the catalytic sites are immediately close to each other, so they surely will exert the synergistic promotions for the ICCC. And here, the suitable bonding CO2 is very important, because we want to see the adsorption reversibilities. And here is we use the calcium oxide as the substrate and the nickel as the catalytic sites to see the ICCC looping performance. And after synthesis, the nickel calcium oxide DFMs, we use the temperature programmed surface reaction to see the different behavior in comparison with the pure CaO. And here in the CO2 flow, we can see there's almost no different behavior, because the CaO changed into the carbonate and changed into carbonate. But in the CH4 flow, methane flow, they show quite different behavior. For the pure CaO, there's almost no changes. But for the nickel DFM, with the nickel catalysis, they should obvious decomposition of methane, and hydrogen was produced. That means nickel can be a good catalysis for the methane dissociation. And for even more, after the CaO, these two samples was CO2 pre-adsorbed, and their behaviors are absolutely different. For the CaO, for the carbonate, for the calcium carbonate, after 700 degrees C, they begin to decompose and release CO2. But here, we haven't seen any signals of CO2. CO2 is here, black one, and only with the hydrogen and the CO was observed. That means the dual functional materials are quite different from the CaO. To understand that, we establish a model with the four nickel cluster supported on the calcium oxide, and do the DFT calculations of the absorption and the desorption routes of CO2, and each steps have different intermediates. Also about the absorption and the desorption routes of methane, we summarized here. So for the CO2 active after the sorption, CO2 is activated as a CO2 star by calcium oxide, and the direct dissociation to the CO star, CO and O is impossible because the energy gap is so great, and but with the hydrogen assisted, when hydrogen star, that is the overflow from the nickel side to the nearby of CO star, they can form COO and give the energy barrier here. Although it gives the energy barrier higher than this one, but the following decomposition is very easier. So this blue line, this blue route is represent here is the favorite route, that is at the hydrogen assistant CO2 dissociation route. Meanwhile, we also found the methane dissociation route summarized here. For the dehydrogen route is this one. But in compared with the OH star assistant, we can find it's much easier to by this red dissociation route. That means by deep dehydrogen in this way, they will produce the coke carbon deposit will produce them. But here, if we go in this way with the OH assistant, that is the overflow of OH produced in the CO2 conversion, can actually accelerate the CH4 dissociation. And we combine these two processes in one circle, in two circles. The red one is CH4 decomposition with the OH here, with the OH produced from the CO2 dissociation. And meanwhile, the hydrogen can participate into this CaCO3 decomposition, and this intermediate COH intermediate is the most important one. And from the Institute DRIFT, we found these intermediates, and which can be verified by the DFT calculation. It's occur at these peaks, and we can find in the Institute DRIFTS. So we can conclusion that at the surface, they will show the synergistic promotions with each other. And based on this, guided by this, we simulated, we synthesis different materials with different nickel loadings, and each one has a porous structure and highly dispersed of particle size, but they have different particle size, nickel particle size. That means different size. That means the different surface area, interface nickel calcium oxide interface are different, and that means we will have different results. And here are some results. Here we can see with proper loading nickel 5, they showed the CO2 adsorption is here about 12 molar per kilogram, and the conversion efficiency is here. The conversion efficiency is about higher than 90%, and the CO2 and the hydrogen and the CO ratio, molar ratio, is almost as when. Although the loading, the nickel loading of tin has a very high CO2 and methane conversion efficiency here, but their STY is lower and more, even worse, some carbon deposit, some coke can be observed after recycle test.
Sorry, Professor Hu, I think we are over time. Can you conclude as early as possible?
Yes. So we made more. We made more smaller particles to make more interface. Finally, we can see the properties can even increases. And so finally, I'd like conclusion my talks. Many thanks for for the financial supportings, and especially this year we also obtained the Natural Science Foundation, and hope this is 2011 we have established a demonstration for the CO2 capture, only for CO2 absorptive capture, but maybe next year we will have ICCC demonstration. So thank you very much.
Thank you, Professor Hu. I think that's very excellent. So a great contribution to this scaling up. So you have this pilot scale and also the DFT calculations. That's also excellent. And thanks. Unfortunately, due to time limit, hopefully we can have a proper conference next time about ICC. You'll have more detailed discussion. Yes. Thank you.
Yes, I want to stop the, yes.
Yeah. So next presentation will be given by Dr. Melis from University of Surrey, UK. Melis? Oh, you're already here. Great, thank you.
All right, thank you very much for the invitation and for organizing this workshop, Chunpei. It's really great to see such good attendance and interest in this area of integrated carbon capture and utilization. So my talk today is going to be on the briefly updating on what I've been working on in my group at University of Surrey with regards to designing dual function materials for integrated CO2 capture and conversion. So you can see here what the University of Surrey, a little bit about where I'm located right now in the UK. My background in this topic goes back to about 10 years ago when I was a PhD student in Professor Bob Ferrado's lab. We together developed the dual function material for capturing CO2 directly from flue gas and converting it to methane in a single reactor operating under isothermal conditions. So this was a calcium ruthenium based dual function material. Methanation is particularly an exciting application because it's got this nice exothermic reaction that we can use to regenerate the adsorbent under isothermal conditions. Since then, my group has been focusing on a lot of different areas. So in particular, I'm really interested in expanding the application of dual function materials to supply basically any carbon containing chemical that we're currently using. But that's not such an easy research endeavor because CO2 hydrogenation catalysis in itself presents some fundamental challenges that we're trying to address in the catalysis community. So that's why my group's efforts are focused on developing new catalysts for CO2 conversion, and then which can become dual function materials. And we're also trying to progress some of the operating parameters, well, some of the performance parameters related to dual function materials. We also do a little bit of plastics capture and upcycling because we view this as part of the broader carbon cycle problem, but I won't be touching on that today. Okay, so I'm going to present one recent update on our work on dual function materials, which is the switchable dual function materials that we've developed recently in my group. What we're looking at here is that there are three reactions that can be performed at ambient conditions or ambient pressure conditions with respect to CO2 utilization. These are the dry reforming of methane, which utilizes methane as a co-reactant for CO2 reduction. Reverse water gas shift competes with CO2 methanation. We know that they have different conditions favoring reverse water gas shift and CO2 methanation. So our thinking with these switchable dual function materials was to devise DFMs that could be considered to be future-proof. And what we mean by that is we have a diversity of CO2 containing streams, and we also have we're going to have access to a growing supply of renewable hydrogen, which is what the reverse water gas shift and CO2 methanation schemes are typically considering as the hydrogen source. But there is a ways to go before we can have access to this green hydrogen. So it might, but we already have hydrocarbon resources that could be at our disposal, such as, biogas has been mentioned today. So what we're investigating here is that can we make dual function materials that are flexible in terms of using either hydrogen or methane, allowing us a smoother transition to a renewable hydrogen-based economy. But also we're looking at can we achieve product flexibility? In other words, making methane, which could be a great way of decarbonizing residential heating in the short term, but also transitioning to making syngas when needed to supply some of the more transportation fuel needs and other chemicals. So this was the idea behind switchable dual function materials. We found a nickel ruthenium catalyst that, upon changing the temperature and the source of reactant from hydrogen to methane, it does perform quite favorably for methanation, reverse water gas shift, as well as the dry reforming of methane reactions. Here I'm showing steady state catalysis data for these three reactions that I just mentioned. But what we've done since then is to translate this by incorporating an adsorbent component, which would be sodium, potassium, and calcium, to develop dual function materials that can be used for all three of these reactions using just dilute sources of CO2. So here, what we've done is just to do proof of concept with a dilute 10% CO2 in inert gas stream. And what we've done is we performed CO2 methanation at 350 degrees after CO2 capture. And then we raised the temperature to 650 degrees to perform reverse water gas shift on the same material after CO2 capture. And then we performed another round of CO2 capture followed by dry reforming of methane just by switching the feed from hydrogen to methane. And I'm happy to give more information about this during the discussion session. But basically, our main finding was that these catalysts, nickel ruthenium-based catalysts, when transformed into a dual function material by incorporating a sodium, potassium, or calcium adsorbent, they are able to perform all three of these reactions, provided we operate at different temperatures and different feeds. So this was a nice proof of concept for us. We haven't optimized the operating conditions. We have some evidence that we actually don't need to operate at the same high temperature conditions for some of these reactions that we would under steady state conditions, because dual function materials, we have to remember, operate at under dynamic conditions, which change the kinetics of reaction. Okay, so one finding as part of this study that was really intriguing, and this was forming a lot of the basis for our future work, happened when we performed temperature program reduction on the precursors to the dual function materials. So this was a rather surprising finding. So what we do when we synthesize these DFMs is we start with nitrate precursors of nickel, ruthenium. We first start by calcining the adsorbent precursors, and then we impregnate the material with nickel and ruthenium, nitrate precursors. And then after that, we do another round of calcination to decompose the nitrates to produce oxides. And then, nickel ruthenium alloys, they become activated in hydrogen for catalyzing these reactions. So what we did before performing the experiment that I just showed you was to identify a suitable reduction temperature for these materials. We performed temperature program reduction on the oxidized precursor to the dual function materials. This showed a very interesting set of results, which was that we were expecting to look at this, water production and say, here's a good temperature to reduce our DFMs. But in addition to this, what we saw were products containing carbon. We actually saw that we were able to make methane directly on these dual function materials that had only been exposed to air. We also saw that 2 of these dual function materials were also able to produce CO. So the only source of carbon for these products could be carbon captured from the air. So we were able to see that our DFMs in their oxidized state were capturing CO2. They were becoming partially reduced initially. The nickel ruthenium was getting partially reduced, after which it was able to catalyze the conversion of this direct air captured CO2. So this was a really interesting finding. And another thing that we observed was on 2 of these DFMs, we saw CO production from captured CO2 and hydrogen before we saw methane production. So this was really interesting because, as you might be guessing, reverse water gas shift is favored at higher temperatures compared to methanation. So this was our proof of concept study, which opened up a lot of questions that we're investigating currently. And what I see as the research needs in the development of DFMs is, one, we need to really focus on realistic flue gas and direct air capture applications, because as I showed in my previous slide, we can get unexpected activity behavior when we actually expose the materials to oxidizing conditions. And that will be, we have to focus on realistic CO2 capture applications for that reason. We need a fundamental understanding of captured CO2 reactivity. We're getting hints on these materials of different CO2 binding sites affecting the product formation. So we need to get a handle around that. We need to form structure activity relationships during dynamic operation. So in the catalysis community, we're doing a lot of great work on characterizing catalysts in operando under steady state conditions. We need to be doing more of that for dynamic operation for the DFMs in order to be able to design new materials. And finally, our adsorbents need to be designed for application as well. We saw in some of the previous presentations that there's a very diverse range of CO2 capture applications that we could be using. So if our applications direct air capture, we need stronger binding at ambient conditions. If our applications, post combustion, we might need intermediate temperature or high temperature adsorbents to be able to catalyze high temperature reactions as well. And then finally, what we need, I've only written nanoscale here for process intensification, which is what we're doing. But actually, we need a way to optimize these materials and operating conditions across the scales. So everything from nanoscale optimization of material composition to designing our reactors, basically, which could be done by some of the nice, utilizing some of the nice modeling work we also saw today in the presentations, but also going up to things like superstructure optimization to see how our DFMs integrate with the larger energy landscape. So that's what we're working on. I want to just quickly acknowledge, I've been showing the PhD student Angie Mercur's work today, but we're a growing lab with a lot of emphasis on dual function materials. We have good support from our funding agencies to develop DFMs for different reactions than what I'm showing today. So very excited to work on all those fronts. So thank you very much.
Thank you, Melis. That's great. It's excellent. Because ICC always sometimes see surprising results. Yeah. I think Bob is doing a lot of work about the DAC with methane production, but your work also shows that the potential of DAC with CO production. That's actually is what we are doing now in our group. That's excellent results. Thanks. Also, due to the time limit, we're going to move to the next presentation. Thanks, Melis. And I think next session will be chaired by Dr. Hui Zhou from Tsinghua University. Hui Zhou is just recently establishing his team at Tsinghua University. He also is starting working in the ICC area. Yeah, Hui, you can, and thanks for chairing the next session.
Thanks, Kunze. Our next speaker will be Professor Robert Ferrado from Columbia University, I think Department of Earth and Environmental Engineering, which I have been worked there before. Hi, Bob, are you here? Hi, Bob.
was there.
I think, yeah, here, if you,
There we are.
hi.
Okay. Sorry
Yeah,
about that.
Yeah, you can start to share.
Okay. Okay, well, good morning or good afternoon, I should say, and good evening to those as well. Very nice presentations. I'm so happy to see that the CO2 capture technology and conversion is beginning to expand into so many different areas, and I think this is very encouraging. We began most of our research, and Dr. Duar was one of the initial pioneers in the development of this technology. We effectively started doing flue gas adsorption and conversion in a single material, which we call the dual function material.
Sorry, Bob. I think your screen is not shared now.
Oh, it's not. Oh, I'm sorry. I'm sorry. Yeah. Let's see. Okay, I guess I got to shut this down. Let's see. Okay. I'm sorry about that.
Yeah, no problem.
Is that better?
Okay. Yeah, I think it's come. Yes, great.
Okay, great. Well, as I was saying, by the way, this is Manhattan, New York City. Columbia University is located right down here. The original work that we began to do with Dr. Duar as her PhD thesis was to look at the flue gas capture of CO2 using a dual function material, which is composed of an adsorbent and a catalyst supported on a high surface area material. We did quite a bit of work in that area, and then we migrated over to what we call DAC, or direct air capture, mainly because of the Department of Energy was very interested in looking at removal of CO2 from the air. So our program is effectively looking at the removal of CO2 from the air using dual function materials and scaling up the technology. And I have a number of things that I want to show you related to the scale up issue. Let's see why. So first of all, in order to investigate whether or not a material will function in a real environment, you obviously need to test in a real environment. And because our program is to scale up, we have to develop some type of models or roadmap in which we could look at how our materials would function in direct air capture as a function of the different ambient conditions that exist based on location, based on time of the day, and naturally based on season. So the DFM process, as has been described, obviously is to take carbon dioxide from the air and effectively look at the ambient conditions, which include obviously oxygen and naturally which include moisture, and then do a temperature swing where we could make methanation. Now, the purpose of making methane is that methane is a precursor to making a wide variety of different types of materials via syngas. There is, in the US right now, there is a $130 tax credit for every ton of CO2 that is removed, followed by producing methane. So there is a real incentive to making methane from CO2, and the technology, as I'm sure you all know, is fairly well known. So our roadmap was to begin by saying, okay, let's do some experiments where we simply do adsorption from simulated air, which contains oxygen and essentially relative humidity here of about 90%. Naturally, because it's air, there's oxygen present as well. So that's more or less our standard state. And we would then do a variety of testing for CO2 capture and methanation at a condition indicated here by the star. And we did that for about 250 hours, which represented literally 30 to 40 cycles of that reaction. And then we would go to a higher temperature, such as 40 degrees centigrade, which would be representative of a very hot summer day. We have a relative humidity of about 28%. By the way, this corresponds to about 2 mole% in the air. And we would evaluate again at the conditions of absorbing at 40 degrees centigrade with 28% relative humidity. We operated for roughly 100 hours, which may have been maybe 15, 20 cycles. And then we would return to our original temperature as our standard to see whether or not there's been any change in the performance. And I'll show you some data where we've been able to establish that the material is certainly stable. And then after that standard condition, we would then go to a colder condition, which would be for effectively 0 degrees centigrade with 0% humidity. And we would operate for a certain length of time. And then we would again return back to effectively our standard condition of 25 degrees, 90% humidity, again, to see whether or not there's been any change in the overall performance. And I'll show you some of that data in a moment. And then finally, we looked at what happens if indeed you operate not with humidity present, but what happens if you have no humidity present? And that turns out to be a very interesting area that deserves a lot of new attention. So that's been our so-called experimental roadmap, trying to effectively look at extreme conditions of temperature and humidity in order to see how well our material can manage that. So all of these conditions, and the very early thing we recognize is that in bringing in very large volumes of air containing a small amount of carbon dioxide, you will have to process so much air that pressure drop will become a major economic factor, because obviously air is at atmospheric pressure, and therefore if you have large pressure drop, you need to apply a compressor or high energy fans, and that's unacceptable from an economic point of view. So based on some of my previous experience in working on automotive catalysts, we transitioned over to using monolithic structures that are shown here. These are just a couple of pictures. These are ceramic materials, typically cordiorite, which is a commercially available material used in catalytic converters, both for gasoline as well as diesel engines. The major advantage that they have is that they have very high, what we call open frontal area, which means effectively very low pressure drop. And therefore, 90% open frontal area translates to very, very low pressure drop for all of that air that you must process. In addition to the low pressure drop, you also have a large geometric surface area, and that large geometric surface area gives you much more capacity to apply your DFM material to the walls of the monolith, and that's shown here in the bottom right. These are some typical pictures of the channels of a ceramic monolith, and you can see the grainy area represents the cordiorite, the walls, and then you can see this light coating, and if you look down here on the bottom right, you can see a more amplified version of that. And that is where the DFM wash coat material is deposited onto the walls. And it's a very thin coating, maybe 100 to 150 microns. And that means then that you can rapidly heat the surface, which is where the active components of DFM are, rather than simply heating the whole packed bed or the whole monolith itself. So this is a well-established technology. It eliminates effectively any poor diffusion. You get very high effectiveness factors. And as I said, you can get rapid surface heating. And that's part of the scale-up work that we're doing with our engineering company. And naturally, because of the automotive exhaust that has been commercialized since the mid-1970s, this monolithic structures are a very production capacity is very high, very much available. So our materials then have gone through those cycles that I mentioned. So here we show approximately 400 hours, which represents a large number of cycles of performance of CO2 capture under a variety of ambient conditions for direct air capture. And you can see the legend here. The purple area represents the methane produced. The black dots represent the amount of CO2 absorbed, and the star again represents the fact that we're at our standard condition which is effectively 90% humidity. And then you have some CO2 that you lose during the heating, which I'll be mentioning in a moment. And then you have a little bit of CO2 that you lose during the purges, from where you move from the air to addition of hydrogen. You need an intermediate nitrogen or a vacuum purge in order to avoid mixing these. So what this shows is that in our standard condition here, and you recall we worked for about 250 hours establishing this, we see a certain amount of absorption of CO2, methane, and unfortunately, because of the temperature swing that we do in the laboratory, we lose quite a bit of the CO2 during the desorption. But in any event, that's an engineering problem that we're addressing with our engineering partner, and I'll describe that a little bit more about that a little bit later on. So then we go to 40 degrees centigrade, and as you go down to 40 degrees, if you go up to 40 degrees centigrade, because of the thermodynamics of absorption, which is exothermic, you get a lower amount of CO2 absorption, and you get methane produced, and you get some CO2 removed. And then you go back to the standard condition, which is the 25 degrees centigrade and 90% relative humidity. And you can see we've got effectively the same amount of CO2 absorbed, roughly the same amount of methane produced as well. And then we go down to 0 degrees centigrade. And at 0 degrees centigrade, which represents a winter temperature, again, you see a significant decrease in the amount of CO2 absorbed, which is contrary to what we would expect from thermodynamics. And that's all because of the fact that water is no longer present in the gas phase, and water has a very positive effect on enhancing absorption, which is part of what we've been studying now recently. And now after the 0 degrees, we go back to 25 degrees. So after 400 hours of testing, probably 150 or so cycles within all these different ambient conditions, we still get the same amount, roughly the same amount of absorption, the same amount of methane produced. So it shows that the particular catalyst material that we're using, which is shown here, is ruthenium sodium alumina, which is deposited on, in this case, a Japanese monolith called from a company called NGK. And this is the wash coat loading, 1.4 grams per cubic inch. It's a 600 cell per square inch, which gives us that high geometric surface area, and a thin wall of 2 mil, which also helps contribute to relatively low pressure drop. And that gave us, over this whole cycle, stable performance. And that's where we are now from the point of view of our materials work. The remaining part of our program obviously is related to engineering. I'm not at liberty to get into that right now. We are scaling this technology up. Expect to have larger bench scale reactors operating at our engineering partner. It's already actually being, one of them is already in commission, and another one is almost in commission. And then we're hoping that we'll have some actual demonstration pilot plants operating probably in another year and a half or so. So that's all I have to say right now. And I would mention that none of this has yet been published. We are in the presence of currently preparing publications on this. So I'll leave it at that point right now. And if there is a little bit of time, I would be happy to answer some questions on this.
Thank you very much, Bob. Yeah, thank you for the excellent talk. I think 12 minutes is too short for the presentation of your whole work, because I know you are one of the earliest group working on ICCU, and glad to see that you are moving to the more challenging part of direct air capture and combination with ICCU. Okay, thank you very much.
Thank you. Thank you.
Thank you. So then we will move to our next speaker. So our next speaker will be Professor Bo Jin from Hunan University.
Hello, can you hear me?
Hi. Yeah, you can share.
Okay. Thanks for the Professor Zhou's introduction. Okay, I'll share my screen. Can you see my screen?
Yes. Yeah.
Okay. Firstly, I want to give thanks to the Professor Wu for invitation for this CCST ICCU workshop. My name is Bo Jing, come from Hunan University. The topic of my presentation is chemical looping, CO2 capture, and the ensued conversion. My presentation will have these three parts. The first is backgrounds and the motivations, and then is chemical looping, CO2 capture, and ensued conversion. In this section, there's two parts. The first is integrated CO2 capture and reforming, and the second is integrated CO2 capture and reverse water gas shift. And lastly, finally, I will give the conclusions and outlooks. As we know, CCUS is one of the effective pathway to deal with CO2 emission, the issues of CO2 emissions. However, for the conventional CCUS route, you will see that there's the CO2 is captured from the industrial and then the compressed transport, and or it will be for the storage or utilization. However, for this road, there's some issues. The first is this is a complex flow sheet, and there's no efficiency to convert CO2 into valuable chemicals. And this road is also high energy penalty and high device cost. Also, the CO2 is compressed and transport. There's possible safety risks. If we can transfer CO2 immediately into valuable chemicals, we can eliminate the compression, transportation, and storage. We call this for the capture, CO2 capture and ensure conversion road. For this road, you'll see there's also have some advantages. The first, this is an integrated process because the captured CO2 can be immediately converted into other valuable chemicals. This is ensure conversion, and this process high efficiency. In this process we can use no CO2 purification and compression and transportation. So how to realize this process, this road? Chemical looping technology provides the possibility because this chemical looping is intensification technology. It is a combination of reaction and separation. You will see here, if the chemical looping is used for CO2 capture and CO2 conversion, it will be looking like this. Chemical looping can divide one process into two or more processes where the cycling of the metal oxides. If we use it for CO2 capture, we can use the calcium oxide. It also means the CO2 sorbent. And if we use it for the CO2 conversion, we can use the alkyl carriers to convert CO2 into CO. As we know, for this chemical looping process, the metal oxide, the iron oxide, and the calcium oxide are the promising materials due to its high storage capacity and high low economic cost. So we proposed one process that is chemical looping CO2 capture and ensure conversion by combining these two materials, sorbent and alkyl carriers. In this process there are three steps. The first is CO2 capture from flue gas. It is also called the combination, and then it's reforming. We convert the machine into the syngas, and then we generate the metal oxide and to finish one cycle. For this process, they have one advantage. It uses the machine and CO2. These two are greenhouse gas. And we use the catalyst is the transfer metal oxide with no economic cost, and the product is the syngas. It is very important the raw materials for the industry. In order to verification this process, we firstly use the physical mixture of calcium carbonate and iron oxide, alumina oxide. You will see here, when combined these two materials, it has enhanced the reforming reactivity to produce hydrogen and CO. And we also performed his kinetical performance. You will see that there's deactivation by the catalyzation. You will see that there's the formation of spinels no activity spinel oxide, and also there's some particle centering and also carbon deposit. So these materials should be improved. And we also examine the reaction pathway, how these two materials to use for this integrated process from the XRD and other the pathway possible reaction pathway. You will see that these two materials are the combination of the calcium carbonate reforming and the partial oxide reforming. And the sorbent and oscillars had some synergy effects. This possible reaction pathway is here. Firstly, is a calcium carbonate decomposition and the iron oxide for oxidation, and then there's dry reforming and partial oxidation, and then there's iron reoxidation. But there's a deactivation due to the formation of no active substance. In order to improve this material, we developed the LDH derived calcium iron magnesium material. The motivation is that we want to motivate the structure to improve its reactivity and stability. Here we'll see that XRD and the SEM. This is the precursor of calcium iron magnesium. It has the layered structure, and after the calcination, you'll see there's calcium oxide and iron oxide, but there's the interaction between the two materials. But it provides two active sites, the CO2 sorption and oxygen carrier. After reaction, there's the formation of solid solutions. This is one of the reasons for deactivation. By comparing his reactivity, you'll see there's also enhanced the reforming activity by calcium iron magnesium compared to the calcium magnesium or iron magnesium. From the calculation, the deactivation meaning derived from the phase change from these two materials to this phase to this one. And also there's no show here is the particle centering or carbon deposit. By comparing to the conventional compensated material, our ADH derived material has higher sensitivity to hydrogen and CO. The reason is that this material has a better morphology. And for the copper-replaced material, it has no active phase formation. So our digital material has the higher activity. As we know, we propose this material, but this material is 3 reactors, and so his flow sheet is complex, and his temperature actually is serene. It is not isothermal. So we introduced Nikon to develop this calcium iron Nikon bioformation materials to optimize the reaction configuration. In order to confirm this optimization, we developed this material. This is XRD for as consent after hydrogen reaction, after mass reaction and CO2 reduction. From this calculation, you will see for this fresh material, it has calcium oxide, iron oxide, and nickel oxide. And there's the monomechanical zirconium oxide. After hydrogen oxidation, there's this is iron and nickel. And after mass reaction, there's also nickel. And but the iron oxide maybe is there's iron O. And after CO2 capture, the iron oxide can be recovered. For this SEMN, there's with increasing the nickel oxide, you will see there's some fine particles. And for the texture property, there's nickel has no effects on the surface area. For the reactivity, firstly we tested his CO2 sorption capacity. You will see that all the materials shows the CO2 capacity larger than 9 more CO2 per kilogram. and his retention rate is larger than 80%. After we changed the reacting agent to myrcene, his CO2 absorption capacity and the retention rate decreases. This is because there's a carbon deposit, but his desorption rate is increased. Sorry. We also test his CO2, the production of CO and syngas. You'll see that for calcium iron, there's no CO, is the red one. There's almost no CO production, but introducing nickel, there's improved CO production and increased risk nickel loadings. And during the CO2 conversion half cycle, you will see that this one is also no activity. And for the syngas production, you will see that the hydrogen, the CO amount is larger than the hydrogen. It's because there's some side reactions. I will introduce in the next slide.
Sorry to interrupt. There's maybe around 2 minutes left, so maybe.
Oh, okay. I will try fast. Sorry. Yeah. This CO during the CO capture is driven from the carbon deposit, and there's also still after cycles there's carbon deposit. I saw that. I see that. I saw. There's a reverse water gas shift occurs because you will see the CO is larger than the hydrogen. We proposed the process magnitude. Also, we changed the machine to hydrogen. We proposed this chemical looping CO2 capture and ensure the reverse water gas shift process. And we developed materials and checked his capacity, CO2 storage capacity, and also storage capacity, and test his reactivity, and shows that this material is a good, is a promising material. Okay, I will give a conclusion. Firstly, this chemical looping for integrated CO capture and conversion is proposed. It's a CLICCC. We tested the fixed mixture and the biofunction materials for this process, and we automate this process while the biofunction material design, reaction configuration recognition, and reaction scene change. Our further research will focus on the developing efficient biofunction materials, reactor design, and system integration. Thank you.
Thank you very much. Thank you, Professor Jin. Yeah. Yeah, it's very interesting to see the work of the combination of the chemical looping and ICCU. I think a lot of work can be done in this area because there's a lot of tunable capabilities. Yeah, thank you. Very inspiring work. Thank you.
Okay, thank you. Any questions?
I'm afraid we don't have a question answered directly.
Okay.
But any questions can leave to the chat session. So maybe you can pay attention to the chat session. Okay. Thank you.
Thank you, everyone. Everyone.
Thank you. So our next speaker is Dr. Yafei Guo from Nanjing Normal University. Hi.
Okay. Hi, Professor Zhou.
Hi. Yeah.
Thank you for Professor Zhou for your kind introduction. Hello, everyone. This is Dr. Guo from Nanjing Normal University, and I'm honored to be here to attend this workshop to share our work about ICCU. Our group has been focused on.
I think the PowerPoint is not shared now.
Oh, sorry. I'm sorry.
Yeah, great.
You can see. Okay.
Yeah.
Our group has been focused on the preparation of liquid calcium-based and liquid magnesium-based DFMs for high temperature and intermediate temperature ICCU applications. And this is outline of my presentation. For the sake of time, I will not give the brief introduction about the general background. And firstly, we have prepared the liquid calcium DFMs for high temperature ICCU RWGS application And the DFM is prepared using carbide slag as the calcium source. And to improve its CO2 uptakes and the CO yield, we have employed the strategies of propionic acid leaching and the citric acid compensation. And from the SAM image and the texture properties, we found that the propionic acid leaching and the citric acid compensation have improved the porous structures of the DFMs and improved the surface area and liquid dispersion, and as well as the fine particles and uniform dispersion of the particles. And then from the experimental test, we demonstrate that the propionic acid leaching and the citric acid compensation have worked synergistically in improving the CO2 uptakes and the CO yield in ICCU. And the mechanical demonstration illustrates that these strategies have endowed the catalyst or the DFM with expanded pore structures and facilitate gas diffusion and uniform liquid dispersion. Also, this strategy has also endowed the DFM with immobilized liquid metallic ions, inhibited liquid crystals and growths, and minimized the liquid particle size. These altogether have improved its CO2 conversion and CO yield. Also, we have adopted the strategy of metal oxide doping to further improve the ICCU performance of liquid calcium DFMs. And we found that the column doping has improved the density of the basic size. And with the increase of the column content, the ratio of the strong basic sides have improved, which means that the basic sides have been transformed from the weak basic side to the strong basic sides. And these have further improved its CO2 uptakes. And also we found that the column doping has also increased the oxygen vaccines in the DFMs. And also, we have adopted binary metal oxide doping to further improve its CO2 conversion rate and working stability for CO production. And we found that the DFM doped with 6% of the column and 6% of cerium oxide possess the CO2 conversion of 72 and a lower decay rate of 12% for CO yield. And the calculation results reveal that by doping the serum into the DFMs, the percentage of the oxygen vaccine increase, and the doped serum oxide interact with the calcium oxide and also the lithium to form solid solutions. And this will also create some more oxygen vacancies. In addition, the calcium oxide also interact with the column oxide to form this solution, which act as a stable physical barrier to prevent the crystal sintering and particle accumulation, which also improves its working stability. And the SEM image shows that liquid particles are uniform dispersed on the surface of the scalene. And this will also favorable for its CO2 conversion. Another part is the liquid magnesium DFMs for intermediate temperature ICCU methanation. And we know that the ICCU process depends heavily on the reduction of the liquid species. And we also found that the reduction of the liquid species often occurs at a very high temperature of about 650 centigrade. And while the methanation temperature range might be around 300 to 400 centigrade, and this initial temperature swing makes the process rather more complicated. Also, we know that for magnesium-based adsorbent, its high CO2 uptakes depends heavily on the doping incremental salts. While incremental salts might be sensitive to temperature, while this high reduction temperature might result in the loss of the incremental salts. So it is better to achieve liquid reduction at a mild temperature, especially under isothermal operating temperature about 300 or 400. In this way, we have investigated the effects of hydrogen concentration and reduction temperature on the ICCU performance of incremental salts promoted liquid magnesium DFMs by considering these conditions. And the results shows that the increase in hydrogen concentration exerts no significant effect on the CO2 uptakes, while the increase in hydrogen concentration increases the methane yield. And the increase in catalyst reduction temperature to some extent will decrease the CO2 uptake, while it will increase the methane yield. And we have also give some of the characterization results. The XPS results indicate that with increase in hydrogen concentration and the reduction temperature, the percentage of the metallic liquor increase. And this is beneficial for promoting CO2 conversion. And hydrogen TPR results indicate that with increase in hydrogen concentration, the alpha peak for surface liquid oxides tends to shift to lower temperature, which means that a higher hydrogen concentration makes the reduction of the liquid speech more easier. And from the XPS results, we also observe that with the increase in reduction temperature, the ratio of the oxygen vaccine increase, which is theoretically very beneficial for improving CO2 uptakes. However, we observed from the TGA curves that a higher temperature has induced the loss of incremental salts at higher temperatures, and this should be responsible for the decline in the CO2 uptakes. So from this point, we think that in order to prevent the loss, to prevent incremental salts from being evaporated, and it is desirable to increase hydrogen concentration while in catalyst reduction. In our another work, we found that liquid and the serum oxide catalyst shows very high CO2 conversion, even exposed at 300 to 400 centigrade. And the TPR results also evidence that the catalyst can be fastly reduced at a low temperature 300. So we coupled this catalyst together with the incremental salt promotes magnesium adsorbent for ICCU methanation application. And we found that this DFM reduced at a medium temperature of 300 centigrade exhibits very better CO2 uptakes and methane yield. And we also demonstrate its underlying mechanism. We think that the addition of serum oxide has induced more oxygen vacancies, and these oxygen vacancies works together with hydrogen concentration to promote liquid reduction from the trivalence and the divalence to the metallic liquid species. And also the presence of the oxygen vacancies also promotes CO2 adsorption and conversion. And lastly, we should talk about some challenges in this field. The first is the working stability in real flue gas containing oxygen, water vapor, and acid impurities. And a previous work indicated that the species of NOx even can be catalytic into ammonia over the ruthenium catalyst. So the catalyst deactivation mechanism should be very complicated. Thus, it is desirable to reveal the oxidative deactivation mechanism in stream containing oxygen and water vapor. Also, we should focus on the deactivation by poisoning by acid impurities. More importantly, I think it should be more effective strategies for inhibiting catalyst deactivation should be proposed, so as the ICCU technology can be adapted to different CO2 sources. The second is the trade-off between CO2 uptakes and other indices. In our work, we find that the DFMs doped with the column oxides can exhibit high CO2 uptakes and CO yields, while the DFMs doped with aluminum oxides, although it exhibits rather low CO2 uptake, while it exhibits very stable working stability. I think in most of the reports literatures, the cyclic test is performed in about 10 or 20 cycles. I think the test in cycle numbers existing 100 might be required to further demonstrate its potential in future scale industrialization. The third one is the reactor configurations. And in most of our tests, fixed bed configurations is used by gas switching mode. However, Koska thought that this configuration has the drawbacks of inevitable influence of the residual gas. This will affect the CO2 capture performance in the next cycle. Also, the problem of the unsteady gas diffusion and temperature diffusion in distribution in the reactor should be focused on. Then Koska proposed that fluidized bed configuration might be suitable for this application, while this configuration still face the challenge of the solid circulation and the zero problem at high temperature. Also, we should focus on the catalyst. If catalysts are present as fine particles when packed in fixed bed reactor or fluidized bed reactor, they will face the challenge of obvious pressure drop and illustration problem. So it is desirable to make solid pellets in future. Thus, suitable granulation methods and to prepare pellets with both high activity and mechanical properties should be focused on. Then this is the packing configuration. Herein we mean the catalyst mode, whether the adsorbent and the catalyst is physically mixed or integrated as a total. If physically mixed, the packing configurations, they are mixed directly or mixed in down layer or multi-layers should also be considered, since these configurations will affect both the heat transfer and gas diffusion in ICCU process. Another one is the kinetic matching.
Sorry to interrupt. So I think the time is very limited. So
okay, I speak.
Yeah, short.
The CO2 capture, gas purging, and hydrogenation process should be kinetic matched. So in this field, kinetic field simulation is required. And it's nice to see that scholars in China have been working on to promote this technology from lab scale to pilot scale. And Tian's group in East China University of Science Technology have been working on energy efficient and cost-effective reactors for ICC applications. And also Sun's group in Shanghai Advanced Research Institute has been working together with Bao Steel on the application demonstration project of ICCU to advance its advanced technology from lab to pilot testing. Also, Professor Hu has also worked with the Sinopec China on this project. Very recently, our group has also worked together with Sinopec Nanjing Chemical Industries to develop highly active and stable DFMs and to advance this technology to pilot scale. And the last point is the economic evaluation. And I think a better demonstration of the different routes to well match the practical scenarios is needed. Also, a comparative analysis of the economic benefits considering the product's baseline using the LCA method is used, and this will persuade enterprise to seek cooperation funding for industrialization. And that's all my presentation. Thanks.
Thank you very much, Dr. Guo. I think it's a very good overview for the ICCU, showing different reactions, different solvents, different catalysts. And I particularly like your slides of their perspective. It's very, yeah, it's very inspiring, I think. Thank you very much.
Yes, thank you.
Okay, you can stop the sharing. Our last speaker will come from Chunfei from Queen's University Belfast. Hi, Chunfei.
Can you see my slide?
Yes.
Thanks. I think we are significantly over the time now, 20 minutes over. So I will keep my presentation short. Then we will have roughly half hour for group discussion. So I should go to my first slide. So my name is Chengfei Wu. I'm from Queen's University Belfast. I think instead of I give quite details about our work in ICCU, I will just quickly give an overview about what we've done in this research area. It's an emerging area, and it's excellent. We see some projects now about the demonstration now. That's great. So I think our group, we have a review paper which published in Sustainable Energy Fuel, which is about the recent advances in integrated CO2 capture and utilization. So there's some details there. So I think the slide is my part will definitely be shared with others. So I think we can have more details here. I think currently the ICCU we have three key parts. ICCU integrated with reverse water gas reaction, and then ICCU we integrated with methanation, and also ICCU integrated with dry reforming. There's also other ICC technologies like I think recently I saw some papers they're using ICC for amine solution-based CO2 capture. So basically they add some chemicals into amine, and then during the stripping stage, so they add hydrogen instead of the direct heating. So that is another area. But I think for the ICC reverse water gas reaction, I think is one of the most popular one. Maybe the methanation is the most popular one. Then is the ICC reverse water gas reaction. The dry reforming is the least popular at the moment, maybe because it's too complicated. So in this work, we investigate different support. Like nickel calcium oxide is using different support, zirconium oxide, titanium oxide, sodium oxide. And so the results, sodium oxide, I think the best. Then this work, we did some in situ analysis using XS and MS and IR combined, which I try to get some insights. I think the key method is, I think from there is a nickel oxide can be reduced during the hydrogenation stage. So unfortunately, we didn't get too much insights from this work. The work is published in Separation Purification Technology. And this one is, I think, the previous speakers mentioned we call it dual looping. So we have two loopings here. One is calcium looping, one is chemical looping. So when we have this nickel and iron combined together, I think the result is results are quite interesting. So have promoted the syngas production, but it's also very complicated. I think some fundamental work could be done there to combine the advantages of these dual functions, dual looping. So this is one of our early work, mainly is related about the addition of cerium into the nickel calcium oxide. From here you can see when we add cerium, the stability of the material is significantly enhanced. This is also for reverse water gas reaction. So that is, I think we don't have many papers available in this area about tech economic analysis. We tried and published this paper recently. I think there's still so many assumptions, but it maybe just one of the early studies about the tech economic analysis. I think the key message here is really the hydrogen price. So the ICC, if you use hydrogenation, the hydrogen price is, I think, is the most part. It takes the most part. I can't remember. It's about maybe 80 or 90% of the cost. So I think this is one of our group's key research work. So we try to simplify this ICCU For ICD reverse super reactions, I think our early work is mainly we want a catalyst, we want a solvent. The catalyst normally is nickel based, but we just found that we don't even need a catalyst, just calcium oxide. So we published the paper it's the first paper in carbon capture science technology. I think there should be a significant impact because in this case, you only use calcium oxide. You don't need any other materials. And it's very robust. And so we don't even need to worry too much about the presence of water, presence of oxygen. But actually, the presence of water and oxygen actually promotes this reaction. But then the NOx, SOx, and other pollutants, we don't worry about that because basically just use calcium oxide, very simple. And the conversion is quite high. It's about 75%, 80%. And just use calcium oxide. And the yield is also relatively good. And recently, this paper we published again in carbon capture science technology. We only use marble stone, but very much cheaper material even than the limestone. So it can get 85% of CO2 conversion and very high it's 100% of CO selectivity. So again, you just use marble stone. It's very cheap material. So potentially you can use a fluidized bed as previously mentioned. So fluidized bed. Because you don't worry too much about the materials degradation, the attrition issues, and so we call it a simplification. So we don't need any catalyst, just the stones, different stones. That's what we are doing now. So in our group, we try to understand the mechanisms of this work, why the calcium oxide is good, why the marble stone is good, and we also screen different stones at the moment. So, and the price is very cheap because the stone is very cheap. Basically, you maybe just need a transportation cost because there are so many marble stone powered dust from the marble stone manufacturing process. So in this area, as ICC imagination, we also published a few papers here. So this work mainly focus is done by Hongman Shen, and mainly we just use a nanocluster of nickel. So we try to reduce the size of nickel, and then the efficiency is very high based on the amount of nickel. But again, this is fundamental research. So I think if we use larger scale, like Bob mentioned, if we load that metals on the support, probably I think maybe the idea is that we try to reduce the size of the active sites. But again, we might have the poisoning issues. So this work we investigate different support, use a nanorod, use Rosalium, and then the support. It's very interesting here. We hear different morphologies of this, and the nanorod is, I think, the best. Interesting. I think want to know that we didn't did any further studies for this point here. After 9 or 8 cycles, you can see the conversion of CO2 is almost 100%. The medicine selectivity almost 100%. So it's all 100% at that point. So we are not quite sure exactly what's going on there. So maybe some further study can be done. So very high selectivity, high conversion. And this work is about the different is interactions between the active sites and the solvent. And so we just manipulate the distance between nickel and the calcium oxide. Actually, this work the key finding is that during the carbonation stage, the calcium oxide becomes calcium carbonate. That process could encapsulate the nickels on the surface of calcium oxide. So that is something we could, I think we need to look at. So because the volume change from calcium oxide to calcium carbonate, the deactivation method of active sites also possible. So this work is about the basically use a racine oxide. We invest the different loading of that. And so dry reforming, we just started. I think this work is published by Chang Lei. So their work is about dry reforming. So our recent work is just accepted a few days ago. So we investigated the influence of the water, influence of the basically influence of moisture and influence of oxygen in the flue gas. I think for the reverse capture reaction, the influence of moisture and oxygen are quite limited, but for dry reforming, the influence is significant, especially when there's oxygen. The oxygen could actually oxidize the nickel, and that will reduce the efficiency of dry reforming. So some other activities, I think we have carbon capture science and technology which is, I think, the only journal specifically to promote carbon capture at the moment. And so we have good, I think it's developing well at the moment. So the other platform is we are trying to develop a carbon capture science technology research forum. We have ICCU. Basically, we try to have an ICCU network to promote that. Today is a relatively short webinar, so hopefully we could have a proper conference about ICC in future. So we try to create have a platform to promote interaction in this area. So I just create a LinkedIn group. So I think I posted the link in the chat. So the other place is about science-share.com. In here, we have a specific section which is about integrated CO2 carbon utilization. So under category 1, category 2 have different challenges. So if you select any topic in category 2, then the subtopic category 3 and 4. So we try to group to categorize all the information about ICCU in this website. So it's science-share.com. So I think that's the end of my talk. And I think maybe I can take over to go to the next session.
Yes. I think you can continue.
Okay, thanks, Hui. So I think we probably 20 minutes behind the schedule. So that's some interesting things here. I think the previous talk, I figured gave some very interesting suggestions. I think we have these points I suggest we could discuss. I think first of all, I think we can have a self-introduction from other groups who haven't given a presentation today. And I think we have some, how can I stop sharing? So I think we have someone who volunteered to give a presentation. Mustafa from Nagoya University, are you still here? Okay, I think we just if someone else want to just quick introduction of your group, that's also fine. If you can raise your hand and can give you a very brief introduction. You can raise your hand anytime. Okay, in that case, I will share my screen again. And some topics I want to can discuss. So the name of the ICCU, ICCC. So who wants to start? I think Professor Hu Jun and also the last speaker also prefer to have the ICCU. The idea is, and I think that is CO2 utilization mainly is for CO2 minimization or enhance of oil recovery. And they want to use CO2 conversion to highlight it's a chemical production, it's a chemical reactions. I don't know what we should discuss. I think just maybe say some personal opinions about what do you think. I'm not sure we can have a conclusion today, have a name. So Liang, you want to say something? So Liang Yi, I saw you raise your hand.
Sorry, I just mistouched that button. Hello,
okay,
everyone.
That's fine.
It's a great workshop today. Thank you.
Thank you. Okay. The names and Professor Hu, you want to highlight anything regarding the ICCC?
Yes. I prefer ICC, just I mentioned before that, because the utilization now currently is mainly focused on the geography utilization as ICCU, something like CCU or some CCUS, or even the CCUSU is usually about the utilization of enhanced oil recovery, not the chemical conversion. So if we take the carbon as the chemical resource, and that is exactly the chemical conversion. So so many C there, so I prefer ICCC. Thank you.
Anyone else want to comment? Bob? You are one of the first pioneers for this area.
Well, thank you, and I want to compliment all of the presenters. That I'm so happy to see that DFM is a basic platform for many other things. Our work, as you guessed from my short presentation, that was within 12 minutes, I should say. That our work is very focused on trying to solve the problem of the CO2 in the atmosphere, coupled with making a useful product. And that brings us to some of the more practical issues that we don't normally think about when we're doing academic research. And that is things like pressure drop, things like impact of impurities. And I know a lot of that was mentioned as well. Also in chemical looping, issues related to attrition as material is circulating in a fluidized bed or some type of a bed. I just feel as though these are critical things to be thinking about if at some time you're thinking of advancing this material to a commercial stage. You've got to be able to do testing in real environments, but that doesn't mean that you can't still do fundamental research as well. So that's the challenge that we all have. And as I said, I'm very happy that so many people are doing such nice work in using DFM as a platform and trying to solve this problem that we're all going to be faced with. Some of us are going to face it a lot sooner than others, but I wish all of you very best of luck in all of your research activities.
Thanks, Bob. Melis, you want to comment, especially comment on that title, ICC or ICC?
Yeah, I'll comment a little bit on the title because I think in terms of naming conventions, we tend to give this technology different names based on what specific, emphasis we want to make with our research, right? I didn't come up with the name of ICCU, but I happen to really like it because the way that the chemical industry of the future is going to look very different than what it looks like now. And even with these dual function materials, for example, we're working on applications right now where there's a simultaneous need for the captured CO2 to be purified to concentrated CO2, but there's also a need for some of it to be converted. So if you find multiple uses for it, utilization just means using the CO2. So I say that's a very broad, nice umbrella from a process perspective, in my opinion. But I think and Bob can correct me on this, but I think I coined the term dual function materials because I was so focused on the adsorbent and catalytic component being together at the time. And we were looking very much on a materials perspective. So I actually like all of these names. And if the focus is on chemical conversion only and no use of the material as an adsorbent, which it also can function as, then I also think that could be a subcategory of ICCU, is the ICCC. It's so that's my little bit of commentary on this. But as long as we're moving this to implementation, I think I have no problem with any of the names.
Thanks, Melis. I think, to be honest, it's quite important to have a unified name for the ICC, the ICCU, because that will create a single voice in the world. Yeah, I think we are actually at leading this ICCU or ICC activities in the world at the moment. So from the molecular modeling to the scaling up to the new concept, I think we are leading in this area. But it would be great if we have a common name, ICC or ICC. Also, you mentioned the dual function, DFM. I think we were criticized by some reviewers that it's not dual function materials because you simply, especially when you physically mix the materials together, they say that it's not just one material, it's two materials. So you can't call it dual functional material. So you can call it a combined material, or so it's other tricky name there. Anyone want to comment on the names? Or as Okay, quite quiet. Maybe we can further discuss that. we'll have other issues to talk. And I saw Stefano. I saw your camera is open. Maybe just give us a quick self-introduction.
Well, regarding the name, I think that the problem is that, as Melly said, we have different approach, starting from the material or starting from the process. So, and also the scale that we want to do to the topic, because ICCU is very broad, and we can then specialize it into different subtopics, and then you point to methanation, and also when you have this product in mind, then you find different paths, because you can have dual function materials, and you can have mixed materials that are in a chemical looping scheme. So it is a bit difficult to have a common view on all of that, but I understand your point, and I agree that it would be a good idea to try to find a common cap for all the stuff that can be recognized. So possibly ICCU, it is the broadest one. So.
Thank you, Stefano. I think, yeah, we're going to have maybe a debate about this in near future also.
I think the term utilization, of all the discussions that we heard today, utilization was the dominant one, as opposed to, and I think that really needs to be emphasized, as opposed to those people that want to do sequestration. I know the name ICCU is too broad in many ways, because as someone was said, there's very particular applications where the technology is beginning to mature. I mean, we're seeing many different types of things besides methane being made. We're seeing CO being made. We're seeing other hydrocarbons being made. So I think trying to capture everything in one name or one fraction of a sentence is not my idea of how to, the specialization that we're moving towards. We're making great advancements, and I think that each of them represents its own unique name. DFM was a term that was used mainly because of the material. Now we're moving towards processes. So in that respect too, ICCU is also correct.
Okay, I think, yeah, the name is really important. I think it's important. Maybe I don't think we kind of keen, or kind of maybe we want to maybe keep ICCU is more broad and ICCC. So yeah, I think probably we can have another chat or discussion about that term in the near future. It would be great if we could unify the name. So I think the other name is dual function materials. I think maybe among us, we all kind of agree we use dual function materials, but maybe just a little bit tricky when we have a physically mixed material. The other people say it's not dual function materials. But personally, I think we probably just keep using dual function materials. Okay, it looks like we are kind of okay with this term. Then I think we can have a quick chat about these key research gaps. I list a few here. I think at the moment there's three key areas as we most of covered today. So reverse vertical ship reaction, methanation, and DIM. The temperature also, methanation is relatively low temperature, and reverse vertical ship reaction and DIM is especially high temperature. So the other ICCU technologies like using liquid reactions. Then I think the one thing I want to highlight is this CO formation during the carbon capture stage. This normally has been, how to say, ignored by many researchers. So if we use, like, it depends on the CO2 source. If the flue gas is the CO2 source, we don't want to form CO in the carbon capture stage. Anyone has comment on that? I think how we should remove the eliminate the CO formation. I think probably that's not the key issue when we have the methanation reaction, because the temperature is relatively low. You don't have that much carbon deposited on the surface of catalyst. So in that case, during the CO2 capture stage, also temperature is relatively low. You don't have CO formation. But especially for reverse water gas shift reaction, like if you have a nickel calcium oxide, the temperature is relatively high, 550 or 600, and you're going to have carbon formed on the surface during the CO2 conversion stage. And then in the carbon capture stage, the carbon will react with calcium oxide and becomes carbon monoxide, and that will become a new pollutant in the flue gas.
Mm-hmm. Yeah, I guess just a comment on that maybe is I think this is another one of those aspects where it's so important to look at the mechanism of why we're seeing the CO formation, right? And to investigate fully if this actually is a problem in a realistic application or not, right? Because we still haven't really, I mean, for every material, there needs to be a bit of an optimization of the process operating conditions. And I think in dynamic operation, there might be a ways that from an operating condition perspective that you prevent that coking carbon formation that you see in a steady state application. So this is why I think it's really important to test the material to its fullest under realistic implementation conditions and be able to predict how it's going to perform in a process. Because if you can prevent coking by pulsing your co-reactant and not keeping it at a very high, at conditions favoring coking, then you eliminate that problem if that's the mechanism. So I think that's why we need to work together to do the structure function relationships alongside the process optimization and really mimicking the realistic conditions.
Yes, thanks, Melise.
I would like, maybe I can add that from the engineering point of view, it's not going to be too difficult to get rid of CO by oxidation if you have that stream with oxygen and CO at high temperature. So.
Okay, that's a good point. So even we have the CO produced in the flue gas, we have another stage to oxidize it.
Yeah, and you have the temperature, you have the oxygen, and you can go back to CO2. It's not going to be particularly difficult to do that, even if it sounds a bit strange, but I wouldn't stop for that.
Okay. Yeah, I think it's probably okay, but it's probably very challenging for dry reforming, especially when we have dry reforming reactions, because carbon formation is very common for dry reforming. You might have a lot of carbon produced, then you have a lot of carbon dioxide, carbon monoxide produced in the carbon capture stage. Yes.
But that's a really great point that Stefano was making, because you have oxygen in flue gas and you have oxygen in air. So it's really important, and we keep saying this, is that if you test it under real CO2 capture conditions, that might not be a problem. So the first thing that one needs to do, it's okay to try out few materials with CO2 and nitrogen, but I think one thing to recognize is some of the problems identified at that stage might not be real problems, because the oxygen might take care of it already.
Mm-hmm.
That's great. Yeah, I think that's a good point.
Yeah, for example, I see more problems if you look at the reaction where you have hydrogen as a co-reactant. And if you have species that are undergoing redox cycles, then you're going to consume a lot of hydrogen to produce water across any cycle. So, for example, the utilization of nickel that turns into nickel oxides and back to nickel, high loading of nickel, that means that you will form a lot of water out of the costly green hydrogen that you are supposing to use. That is something that is not commonly addressed as an issue, but I think it is very important when it comes to the sustainability and the economic sustainability of the process.
Yeah. Okay, I think the next issue I want to discuss is I think it's about the capacity of the solvent. Mostly used solvent is calcium oxide based at high temperature. We understand its capacity is quite high. It's higher than 10 millimole per gram of CO2 capture. But I think when we come to the low temperature CO2 capture, like for methanation or medium temperature methanation, I think the capacity really is the issue. Use sodium oxide, I think we get less than 1 millimole per gram of capacity. And magnesium oxide is a common intermediate medium temperature solvent, but itself is really it's just deactivating. Deactivation is really a problem for magnesium oxide. I think for high temperature one, calcium oxide will solve most of the issues. That's fine. It's just a low temperature, medium temperature solvent, like in terms of the capacity. We mainly use sodium oxide and magnesium oxide, I think at the moment, for least low temperature and medium temperature reactions here. So I think there are challenges there. So although the carbon capture itself has been invested for many years, but I think there's still breakthroughs need to be done if we want to combine that with CO2 utilization. So the capacity of CO2 carbon, how to enhance the capacity. For magnesium oxide, it's been investigated many years, but the challenge is still there. Any comments on regarding that? So there's still challenges we still need to do.
I would like to comment on magnesium oxide. I've seen in the recent literature some very interesting results when magnesium oxide is coupled with molten salts. And the problem seems to be that under reacting conditions, you can also decompose the metal nitrates that are your molten salts. So that is something that, for example, prevents the utilization of this approach if you have a very active catalyst. So you cannot make a dual function materials out of that, because your ruthenium or nickel would decompose the metal nitrates, and that's something that it's a pity, I would say, but it could be investigated in more details to try to find out a way to couple the benefits of having the catalytic site and also the molten salts to improve the capacity.
That's a good point. We are also doing something, just started using molten salts. Try to.
In that case, it is very important. For example, if you have the separate materials, the way you mix them, because you can end up with very different results if you have separate layers of materials or if you have mixed pellets. So I think it's a challenging topic that could be investigated in more details.
We have two comments there I want to discuss, I want to address. So I think that one's to Bob. And I think the question say ICCUS. I think that's the main, how the ICCC or ICC contributes to CCUS.
I'm sorry, were you asking me? I couldn't.
Yeah, I think that comment is for you, but we can answer the question. So there's no comments.
Why are we getting so concerned about what to call these things? We're all trying to remove CO2 from either being produced or from the air. I don't know whether or not it warrants all of this discussion on what to call it, to be perfectly honest with you.
Yeah, so I think that question mainly is the contribution of ICCC to CCUS. I think what we are doing now, we just want to utilize the CO2. So eventually, the CO2 maybe need to be stored somewhere, or we just increase, just reduce the speed of CO2 release. I think it's like waste recycling. Previously, I think for CO2 utilization, maybe it's better. Sometimes we call it the CO2 recycling. So waste recycling, everybody understands it. But for CO2 utilization, I think sometimes causes confusion. Okay, I think Homan want to discuss about the definition of dual function materials. how we define the dual function materials. We have 2 functions, but sometimes we have 3 functions.
Yeah, there are actually 4 functions. And we tried to do that in a paper, and one of the reviewers told us, don't do it. Don't make it more complicated. They're just getting used to DFM. so don't.
Yeah, I think that's common sense. It makes it simple. It's called DFM. Although there's many functions are combined, we just call it DFM.
When you put it in a process, many other things happen as well that we've been finding out. And that's why I said there's more than just 2 applications now, or 2 components to DFM. It does other things as well besides just making just an adsorbent and a catalyst. It's also part of a process now. I can't get into much more detail on what we're discussing now for patent reasons.
Yes, thanks, Bob. And I'm not sure how long we want to stay, but I think there's a few maybe. I think at least all this here. Maybe, I'm not sure which one you want to have a quick, detailed discussion. So we definitely want to match these carbon capture and CO2 utilization. We want to match these and the valuable products. I think we mainly focus on methane, syngas at the moment, but my group we try to maybe produce methanol or other products, which is more valuable, but it's more challenging because in the high pressure. Then different CO2 source. I think we are probably many of us are moving to direct air capture combined with ICCU. I think that is a trend. We just recently got a small project for DAC ICCU. Then there's massive amount of work can be done using different catalysts, different solvent. I think it's endless work can be done there. There's so many. And then, of course, to balance the the CO2 capture capacity, the yield and the selectivity of the product, that's also important. And then more economic analysis, even life cycle assessment, scaling up. I think it's great. We see some scaling up activities at the moment. Modeling, molecular modeling, different scale of modeling. I think that's also important. Yeah, anyone want to discuss any point of this?
I guess I just want to make one more comment, and I apologize if I'm talking too much. But the problem of using a adsorbent in a flue gas, particularly a power plant, we did some back of the envelope calculations, and you need capture capacity that is going to be larger than the plant itself. Because these materials, especially if you have a solid material, you don't have that much of a large capacity. And you have that problem of the pressure drop. That is an enormous problem with any kind of a pack bed. Even monoliths, and we did some calculations also on trying to use monoliths. And I think that everything points to flue gas from a power plant is going to be very, very difficult to capture because of the high flow rates, the concentrations, the various components that are present in flue gas. And that's why I think direct air capture may be what we call low-hanging fruit. It may be one of the earlier possible applications where you can control the amount of airflow based on pressure drop and linear velocity and turbulence, et cetera. Whereas in a flue gas, it's just a real flue gas. It's very high flows and very, very large amounts of material that are going to be needed. And so that's what I wanted to just comment. And I know I'm not suggesting people don't work on flue gas, but commercially, it's going to be very, very difficult, I think, to capture CO2 out of a large power plant when you're talking megawatts of energy. Maybe small boilers and things like that, it may be feasible. But there are very significant engineering challenges associated with flue gas.
That's a good point, Bob. Yeah, because the flue gas, basically, the power plant is there, the flue gas flow rate is there. You can't control it that much. But for DAC, you can control the flow rate of air. Yeah, that's a good point.
I mean, most of our early publications were all on flue gas until we began to realize how complicated it's going to be when you do a calculation as to how much you need in terms of the material and what the size of your reactor is going to be and what the pressure drop is going to be. And it's very, and furthermore, we have solar and wind and other sources by which electricity can ultimately be generated. So hopefully we won't be doing combustion of fossil fuels. We'll start transitioning over to some more reasonable renewable energy systems. So the DAC, the direct air capture, is a problem that's going to be with us regardless of whatever happens. We have all this CO2 that's a residual in the atmosphere, and it's got to be removed if we want to save the planet. So, and as I said, it's maybe a little bit easier in terms of you don't have sulfur oxides and nitrogen oxides and all these things in the air. You do have insects and dust. You can usually filter some of them out. But anyway, that's my pitch for why I think direct air capture may be more viable right now. There's no alternative to it. You've got to remove the CO2, whereas there are other options for generating power using renewable sources, so you capture CO2.
Yeah, thanks, Bob. I think
we're a long way off. I agree.
Yeah, I think we're definitely going to finish with, before 3 p.m. here. I mean, within 7 minutes. And I think, Bob, that's a good point. But we also can do ICCU for biogas, you know, from anaerobic digestion.
Sure.
We can do ICCU for syngas from a biomass gasification, which one of my students is working on that. So.
Even fermentation, I think.
Yes, fermentation. Yeah.
Maybe not to make methane, but effectively to remove the CO2 from the effluent there. And there's always blue hydrogen. So,
yes.
You know that also you can remove the CO2 from steam reforming.
Okay, I think maybe the last point we want to discuss is about the future interactions. I'm not sure whether you like the idea we probably could have a CCST ICCU mini conference, like a one-day conference in future, because today we try to cover some scientific outcomes, but the time is very limited, 12 minutes, but I can't say too much.
Yeah, timing is always a problem.
We could even have an in-person meeting, a conference at some time.
That would be wonderful.
So I think everyone agrees that probably there's a need for a potential conference.
I certainly agree.
We also need not internet meeting, but we need to communicate face-to-face. And that may be more easier for us to communicate directly. And some words are difficult to expression. Maybe we need the conference face-to-face.
Mm-hmm.
I'm looking for that.
Okay, so we're going to decide who is going to organize the ICCU conference. we don't need to decide today. I think the atmosphere is that we need a conference, no matter online or in-person conference. So we can see how we can do. But I think we should let that happen as early as possible. Maybe next year, 2023, we should have a conference for ICCU.
I think it's a good idea.
Yeah.
That's great. That's great.
I will come.
Me too.
Okay, that's excellent. Because today we also because we have many students, all of us has many students. So the student should talk to each other and about ICCU. I think the other thing I mentioned is that we have the Carbon Capture Science and Technology, this journal. I think at the moment we have published maybe 3 or 4 papers there about ICCU. Recently, actually, I received a paper submission from another group. I can't remember the name. They investigated the influence of the SOx and NOx on the ICCU. It's quite interesting. So when that's published, I can share that work. In that case, I think that Carbon Capture Science Technology, this journal, could be actually a flagship journal for to communicate the ICCU technologies. That could be interesting. Yeah. And so this is one of the platforms. The other platform is we try to, I think we want to keep this link, keep the have this network to keep this ICCU link. I will try to create a list of participants or a list of the expertise in this ICCU. I can share with everyone, so we understand who is doing what in this area. Personally, we will also try to update the ScienceShare website regarding the ICCU. So I think hopefully our PhD students or earlier career researchers can benefit from that website. We try to categorize the information. For example, if you want to know what's the influence of temperature on a certain material, so we try to categorize the information there. I think probably that's all from my side.
Thank you very much, Chen-Fei, for all of your hard work.
Thank you,
Yes.
thank you, Bob. Thanks for all to join the workshop.
So we will also keep the CCST workshop as a series of workshops. So besides ICCU, maybe if you have other ideas that you want to propose a workshop, so you can feel free to use this platform. And we can also have maybe CCST and Elsewhere with us. So it will be better for that we can keep it like a series of workshop, maybe for different topics like membranes, solid solvents, amines, different things.
Thanks, Clay. Yeah, of course, I think we are not only work on ICCU, we're also working on other areas like bioenergy, plastics, and Malaysia is working on plastics. I just realized that. And also carbon capture, pure carbon capture. I think we all work in different areas. So yeah, we can also have a series of workshops on other areas. Yeah.
Yeah, if you have some basic idea, you can contact Chen-Fei or me, so we can have a further discussion.
Okay. Thank you. Luan, you want to add something?
No, I just wanted to thank everybody and thank you, Chen-Fei. Thank you for all the presenters. We have recorded the session, so it should be available in a while on the same site where you had to join.
Okay, thank you.
Thank you so much, everyone. Bye-bye.
Bye-bye.
Bye.
Thank you.
Bye.